Greetings, welcome back. I want to provide a very simple example. This example is for the sake of clarification. It is not really what is happening in this field, but the example does the job. So let's take a look at this classification problem. We do have 0 and 0, the coordinates of a point, 0 and 1, 1 and 0, -1 and -1, and they belong to one class. 2.10, 0 minus 2.1, 1.6 minus 1.6, they belong to the other class. Imagine we have been able to identify a network, a neural network, that actually can provide the output, the target as we want in the classification problem. Now, this is x1, this is x2, that would be the coordinates. So this is x1 and x2. All of these are going to be a bracket, x1, comma, x2, close bracket. Then you have the edges have a weight, and assuming that these weights have been discovered, they are +1 and -1. You do have a step function, and this step function is going to generate the output. And now keep in mind, because this is +1, so this is +1 times x1, this is -1 times x2. So still the summation applies, except that the coefficient of x2 is -1. So it's going to be x1 minus x2, and that's going to be the f of summation of x1 plus open bracket minus x2 close bracket. So that's the way you could potentially look at. Now, let's map these points onto the 2D space. This is x1, the horizontal axis. This is x2, the vertical axis. For example, 0 and 0 is going to be the origin. 0 and 1 is going to be this point, slightly off the line, of course. 1 and 0 is going to be this point. -1 and -1 is going to be this point. Again, that deviation was not intentional. It happened just by accident. Now, if you go 2.1 and 0, 2.1 and 0, so this is 2.1 and 0. So x is 2.1 and 0. And then 0 and -2.5, 1.6 and -1.6. Now, when we classify this, there is going to be a line in this example, a very nice classification results. You have these these three red dots on one class, and these three empty dots on another class. And you can see this line does the job. Now, this line has a function. The function is x1 minus x2. If you take a look at x1 minus x2, specifically to the other class, you can see that this distance is always greater than 1. Even this one is 0 minus 2.5, so that's 2.5, greater than 2. 1.6 minus 1.6, that's going to be 3.2. That kind of distance doesn't exist here. So if you take a look at this, my function is supposed to be generating as 2. My summation, my input. My input is supposed to be generating as 2. So my net is going to be 2, a very nice indication of separation of the two classes. Now, if net is greater than 2, it's going to be 1. If net is less than or equal to 2, it's going to be 0. So I'm going to say that these 4 points belong to the class 0, and these 3 points belong to the class 1. And then you can say 0 means yes and 1 means no, or vice versa, depending on your experimentation. So this is a very nice example that shows that the neural network can do the job. You could come back and say, listen, this line doesn't have to be x1 minus x2 as equal to 2. You're right. You're absolutely right. This line could potentially be a little bit tilted, and still the classification is going to work. First and foremost, the neural network doesn't have to be unique answer. That's one thing. Depends on the rule book that you have, depending on how you're going to bring the input to the system. Of course, that's going to have an impact. The second thing is going to be, for example, the type of the network that you have. We discussed about different structures of the network. That's going to have an impact. So basically, if the structure is fixed, I would say that potentially this line is going to be the same or similar. Another thing you need to keep in mind is that how did you start learning? Did you start learning on 0, 0 first, then 2.10 next, then 0 and 1 second, and then how did you learn the network? The way you learn it, the way you begin and end it is actually going to have an impact on the weight. True. Do you remember gradient descent? The gradient descent does not have a cut response. It's not a perfect response. It's not going to be a unique response. If you start from here, I'm going to calibrate my Y, my W's differently. If I do these and then I do this, it all depends on how I start and how I continue and how I end. And that's going to have an impact on my calibration of W1 and W2. So true, this simple example shows all of the efficiency as well as the deficiency of the neural network in general, okay? We don't want the coefficients to be above 1, and mainly because of the hardware implementation. Hardware implementation would like to see all of these coefficients to be less than 1. We often go ahead and actually normalize them. We find the maximum and we divide them on that. You could potentially say that these are the same, these networks are the same. True. If you multiply this by 200 and this by 200 and this by 200, and the same goes to 1.3 minus 1.3 and 2.3 minus 2.6, you are going to get the same network. But in terms of implementation, this is easier to implement. So we would like to remain within the means, often around 1 or even less than 1. We could have a very nice problem. That was actually a nice problem we solved on top. This is another example which is separable, linearly separable classes. You could potentially put all of the blues here and all of the kind of a brown on this side, and one line does the job. Isn't that nice? But obviously there are cases that you cannot separate them linearly. It's linearly non-separable classes. Do you want to put line here? You didn't separate. Do you want to put line here? You didn't separate. Do you want to put a kind of a slopy line? You didn't separate. It's not separable linearly. So that's one thing. You could also see this, the simplicity of the example I brought to your attention just a moment ago. You can see that the blues are on this side and the reds are on this side. You could potentially put your finger here and say, this is the cutting line. I can cut the line and have two classes identified. But as you can see, these are mingled. The red and the blue are actually intervened, and therefore you cannot say, okay, this is the cutting line. Keep in mind that we will talk about underfeet and overfeet later down the road, and there we might accept imperfection. This is a perfect classification. When you put your hand here, you made it very perfect in the training set, possibly test set. In validation, who knows? But in this one, even in the training set and test set, you have difficulties. You are going to accept some sort of error, as we discussed in the past, for the sake of doing a job on a lot of other cases. For example, when we say 99% out of 1,000, that would be 990 examples that are going to be working just fine. So that's really important, right? I don't want to go through the rest of the slides, a little bit too mathematics. For those of you who want to have a little bit advanced exposure, a little bit, I would say. This is not really much, but you could potentially take a look at those slides I just passed by. Multi-class discrimination is possible. As we said, you could have, here you have a cell that is going to take care of the three inputs. The three inputs are going to have a relationship with this cell. We are going to say W11, and then we could say W21, W31. If one represents this one, I would potentially say W14, W24, W44 if 4 represents this one. And that's every cell is going to be independent. We can see that this class has nothing to do with this class, has nothing to do with this class from the output point of view. And of course, these W's, the weights are not necessarily the same. So you can see that these weights are quite independent. Therefore, you could view this as a single cell, as a single neuron, and the training is going to be done independently than this one and this one and this one. Yet we are going to call this multi-class, because in the majority of the problem we face in the real world, we are not dealing with a class of yes and no. It's not going to be black and white. It's not going to be two classes. Usually it's going to be multi-classes, such as this one. So this is going to be a case of a multi-class discrimination. And you could potentially say that this one is going to be identified by one of those outputs. So one of these outputs could be dedicated to this one. One of this one, for example, is going to be and the triangular and then the circle. You could potentially say that this one is responsible for one class, one class, one class, one class. You can see something we were not able to do linearly just a few slides ago. For example, this one, we couldn't do this linearly. Now we can do this very easily with a little bit complexity with the multi-class discrimination, and we could potentially classify them. So that's really an interesting output. Single layer are really simple. They could potentially give you results, but the problem with single layers is that their capabilities are quite limited, and the results that they give you are not going to be as much flexible. The problem with single layer, whether you're talking about multi-class or a single class, doesn't matter. The problem with single layer is that this one is a done deal. You can't change them as soon as you have found your maximum optimum point. You cannot change them. There's nothing you could do. But then for the multi-layer, the flexibility is going to be available. So you take a look at this. This is my input. This is my input layer. This is my hidden layers, two hidden layers, and this is going to be my output layers. What do I say flexibility? Well, I can change these W's. With the same event, x1 up to x5, I could change these W's. I could change these W's. Which one is going to have the most impact on my classification result? I don't know. We are going to let the computer to run, and the computer is going to run possibly a day, possibly a week, possibly a month. This is going to take a huge amount of time, even with today's technology, depending on the number of layers you have, depending on the number of cells you have per layer. It's going to be huge. And then that's going to be basically allowing us to train better. It's going to be more flexible, and it's going to be a lot more simpler. Once again, I want to talk to you about the backpropagation. We spoke of the output. You take a look at the output. You're going to take a look at something we call sensitivity. And the sensitivity, what do? You're going to just perturb this W, just a small amount. And then you're going to see what the output is. And then when you take a look at the output, you're going to say, okay, I'm going to go back and I'm going to change this in one specific direction. And then this happens to be the output of this cell. And with that in mind, you're going to go back and change the W1. You're going to perturb W1 if you needed to. This is called backpropagation. And backpropagation is not the same as gradient descent. Gradient descent means the type of sensitivity you have. Backpropagation means let's start from the output and basically reverberate all the way back to the input. Just go back to the input and see what you can do with these W's, what you can do with these W's, right? Now, if you want to do forward, of course, you have these X's in, so you have the input I1, I2 up to B1. You could potentially perturb this, vibrate this. You can vibrate this, perturb this, and then you can potentially see what the output is going to look like. You could do forward, you could do backward. Preferably backward, backpropagation has shown to be a lot better because you know what the output is supposed to look like. The output, the actual value of the output, you already know what it's supposed to look like. So you're going to maintain the input, you're going to maintain the output as in actual output potentially, and then you're going to come back and say, okay, what can I do with the W's to get that? Even if it is not an actual output, but close enough, you could potentially come back and say, I'm going to perturb this and see what I can do to get them right. Usually perturbations or vibrations work if your vibrations is small, very nice. It would be very nice. You don't want to have huge swings on the W's. So that's backpropagation. We talked about forward as well and backward phase. A backpropagation analytics has a forward and a backward, and then forward and a backward. You do this on a number of times until you get the W settled. Remember, we do not have global optimum most of the time. We have local optimum, and our own best bet would be whether the local optimum are going to be very close to the global optimum. We call them near optimum solution. And here is the deal, and that is depending on where your W's fall on the plane. You have W1, W2, W3, W11, W12, W13, right? All of those W's. Depending on how you land on the values of the W's, you could be trapped in one of the local minimum or local optimum, generally speaking. You could even be near optimum, and the other near optimum that you want to investigate and find could potentially be costly. So most of the time, we are going to reserve ourselves to the case that we found at hand and simply let it go. We don't want to investigate too far and we are not looking for perfection. We're going to look for the imperfection, a little bit of imperfection if we have to. Backpropagation has some advantages. It has great representation power, wide practical applicability, easy to implement, and good generalization power, but it has a disadvantage. Learning often takes a long time to converge. The network is essentially a black box. You don't know what it is inside. And the W's, a gradient descent approach only guarantees a local minimum value. You want to have a minimum error. You want to have the least error if possible. Not every function can be learned, of course. Generation is not guaranteed. Generalization, the selection of learning parameters can only be done by trial and error. This learning is non-incremental. To include new training samples, the network must be retrained with all old and new samples. And that's really a pain because as soon as you bring in a new sample, you need to retrain the system. You can't just rely on the W's you just found. And experiment and applications have shown that you need to actually retrain the system. Of course, one or two additional samples should not disturb the network, but if you're bringing in 1/3 of the data set you have trained and tested, then you have to retrain and retest the matter. So this is going to be the part in regard to neural network. I hope you know the terminologies. I know you have the structure in mind. I hope you know what the function is. I hope you know what the loss or error function is. What is our intention? How you can basically learn neural network on an application in mind. But of course, this is a big topic, and I would encourage you to take the follow-up course on this, where they are going to go deeper into all of the manners of optimizations and all of the manners of layers and cells and all of that. I wish you good luck, and we are going to close part 4, and then we are going to open part 5 in the next recording. Stay tuned.